In this section about entropy, we will have a look at how we can quantify how well Huffman coding will work without running it on the text, but just by analyzing the text up front. And we'll come to statements that are more versatile than just analyzing Huffman codes. We've seen Huffman codes are the best possible prefix-free character codes, but we'll look at other compression methods later on. And so, yeah, Huffman codes are the best of this specific family. It's not necessarily the best overall for all sorts of scenarios, but entropy gives us a way to evaluate how well Huffman codes would work on a given text without trying it out, just as an analytical way. So let's start with the definition. That's just something that falls from the sky without much motivation at this point, but I'll try to motivate it, give the intuition behind that definition right after. The entropy is defined for probabilities. So we have here p numbers. They're between 0 and 1, and they sum to 1, so it's a probability distribution. So what that means is p1, p2 up to pn sums to 1. And also each pi is between 0 and 1. That's, well, as you may have seen in other courses, that's probability distribution where we have n possible different outcomes. And the entropy is defined for the distribution. So it depends on these probability weights. And it's just this sum. So we sum pi times log of pi, logarithm to the base of 2, and a minus in front, or this is the formula I think it's a little more intuitive, so I would like you to keep this one in mind. It's pi times log of 1 over pi. So why might it make sense to make this definition? Well, first of all, I've just thrown this definition at you and haven't told you what we'll use it for. The idea of entropy is to have a measure of information content. Now, what's the information content of a distribution? That's a bit unclear, maybe. What we mean by that is if you draw a random sample from that distribution, a single random variable that's distributed according to this distribution, and then this variable will have one specific value. But because it's a random variable, you can talk about expected values. And so the entropy gets at the question of the expected number of yes-no questions you need to answer to nail down the value of this random variable. Okay? So in a sense, if you know this game of 20 questions where you ask 20 yes-no questions and try to nail down a specific thing that your partner thinks about, then this is in a sense what the yes-no questions in entropy also try to do. So let's try to see an example by what I mean by this. Suppose we lay out the probabilities. So this p1 up to pn, I can draw this unit interval, and I can put in the probabilities here. So suppose the length of this, that's my p1. The length of this is p2, and so on up to pn. Because they sum to 1, this has to go up and cover exactly the unit interval. And then the outcome of this random variable is selecting one of these intervals. So in the picture here, there's one of these intervals is red, and that's the one that this variable actually took. Now let's try to figure out yes-no questions that allow us to find out which of these intervals was selected. And so the best thing you can in general do if you start with this interval, at the start, you know nothing. You know the red interval is somewhere in the unit interval, but that's all. And so you try to ask a question that, with one yes-no question, maximizes the amount you learn. So I guess the best and intuitive way of doing this is asking whether the value is left or right of the middle point. Okay? So you ask this question. It's a yes-no question, or well, it's a left-right question. Is it left? Yes, no. Okay. In this case, it's on the right side. And so after the answer to that question, you asked one question and you learned now the interval is somewhere on the right of the middle point. Okay? And you keep going like this. You cut it in half another time with another question and another time and one more time. And then if you know that, if you remember this picture from above, if there were these intervals for the PI, if you've nailed it down to this range, maybe that's all we need, and then you know the value. That's a single interval left. So if the probability here is this distance, the probability of falling into this red range is the difference between the endpoints, and that's 1/16. If that is the probability, then this value here, log of 1 over the probability, is 4, because 1/16 is 16, and log base 2 of 16 is 4. Now, how does this match up? This number of 4 is exactly the number of times we had to cut the unit interval in half before we arrived at that size. That's, after all that the logarithm expresses. And so this quantity that we sum up here is, in a way, the number of yes-no questions you need to make before you get down to this size. It's the number of times you have to cut the unit interval in half before you reach a certain size. And this is what we define as the information content of that outcome, because it took you so many yes-no questions to get there. And then the entropy is just averaging that over all possible outcomes. Each PI occurs with probability PI, or each outcome I occurs with probability PI. And it took you log of 1 over PI questions to find that. That's the rough intuition behind entropy. Okay, that's why this term might make some sense. But we'll put it into more concrete context with Huffman codes on the next slide. In general, if we have a random value, then we ask how many questions do we need to nail down that specific value. And here I identified the value with the position of the interval. So I labeled the intervals from left to right, 1, 2, 3, up to n. And then finding out if the random variable is in one of these intervals is the same as finding if its value is a value I. But no matter what the values really are, you can always draw the probabilities as these intervals in the unit interval. So it seems, at least from this intuition, that we would like to encode a value I, if it has probability pi, using log of 1 over pi bits, because that was the number of yes-no questions we used before. Okay, so far I can only appeal to your intuition that maybe this makes sense. But at least it already is clear that this is not quite possible, because log of 1 over pi might be some real number, definitely not necessarily integral. And so it's a little tough to see how we can create code words with length 1.5. This sounds, if you think of specific code words, there's no binary string of length 1.5, but you can sometimes achieve this on average if you don't have a fixed code word, but you have the option to average things out. Then you can sometimes indeed achieve this. It's something that we won't cover, but there's a method called arithmetic coding that is Huffman on steroids. I don't know. It allows you to do this, to code things with a fractional number of bits. But yeah, we'll leave it with Huffman. So in Huffman coding, we cannot do this. So it seems like as long as we have a Huffman code, we have to somehow round up. And that's also what we see in this result. So let's parse this step by step. We have some alphabet sigma again. So we have characters 1 up to sigma, or A1 up to A sigma. and they have some weights. Again, think of the weights of as relative frequencies or probabilities. And we have a Huffman code. So that's the code from last time. I showed you how to compute that one. And remember, L of the code, that was this expected code word length. So L of E, oh, don't do this to me again. We sum over all the characters. And what do we sum up? The weight of the character times the length of the code word. That was the definition of this L. And now this theorem says I can look at an entropy. So H, this calligraphic H, is what I'll use to denote entropy as defined here. Now we take the relative weights. Okay, so these are exactly the weights, but we divide by their sum. And if the weights are probabilities, then the sum will be 1, and this is just the entropy of the probabilities then. But in general, it's convenient to allow weights so that we can just put in frequencies. I take the relative weights, I compute their entropy, and it turns out that this is a very tight bound for how well Huffman will do, how well the Huffman code works for these weights. The code is at least, uses at least as many bits on average than H. And it turns out H is a lower bound. You can't possibly beat that. And H plus 1 is an upper bound. And that comes essentially from the fact of this rounding. If the entropy tells you, please use 1.1 bits, you can't really do that. You have to round it up. And if you do that rounding up all the time, you essentially lose this plus 1. We'll see that in the proof. Is the statement clear? So you compute a Huffman code for a given an alphabet with some weights. And this theorem tells you quite precisely how long on average a code word will be. If you take a random character, then the expected length of its code word will be between H and H plus 1. Let's sketch at least how we can prove this. There's two parts. The first statement is the lower bound, that L of E is bigger than H. And we will prove this not for a Huffman code E, but really for any prefix-free code, because the statement is true for any prefix-free code. If we have a prefix-free code E, then we can choose weights. That again is just a definition, but it has an intuition as well behind it. So the QI are defined as 2 to the minus the length of that code word. And that comes from the idea that each bit you spend in the code words is something like a question, left or right. And so whenever you spend a bit, you should cut down the probability in half. And so these QI are exactly defined so that every bit cuts things in half. There's something called Gibbs Inequality that shows that if you do this, you get to at most 1. And the intuition is if you draw the trie for this code, remember the code trie looked always like this. We have 0, 1, more edges, 0, 1. And maybe then here in the leaves, you have the characters. Okay, remember code tries, Huffman codes, etc. It was important that the characters are only in the leaves. The alphabet symbols are only in the leaves. And what this says is if you assign a weight of 1 to the root, and then assign half of that weight to its children, and half of that weight to their children, and half of their weight to their children. I think it's clear if you go down one step the weight on one level is always summing to 1. It started with 1, and then you exactly split it in half, so the sum is still 1, and that keeps going. And what you can also show is if you take any cut through this tree that doesn't contain 2 nodes where one is an ancestor of the other, then they also sum to at most 1, because you cover at most 1 level just shifting things up and down. The idea here is you could pretend that these go down 1 more level and then they go all to 1/8. Okay, then no one can read this. If you go down to the level of the deepest leaf, you will have a power of 2, and that is the number of leaves on that level, and those sum to exactly 1. If you combine 2 of these into the 1/4, their sum is still the same. And so if this tree is full, if you don't leave out any nodes, you will actually sum to exactly 1. And you can leave out some leaves, then you sum to at most 1. All that Crafts inequality says, sum is at most 1. Then there's another inequality, Gibbs inequality, that applies here. So this part is Gibbs inequality here. I don't want to prove it, but it's a standard result in probability theory. So let's just use that as a black box. It says when you have something that sums up to at most 1, then you can replace in the entropy formula the p's here by the q's there. That's Gibbs lemma, Gibbs inequality. So we write down the entropy, use Gibbs inequality to sum over the qi here instead of the pi. And this sum is exactly L, just written in a different way. Because here, if you plug in what qi is defined like, then this 1/, becomes 2 to the length of the code word, and log base 2 just takes the 2 to the away. So what you're left with is the sum of the lengths of the code words times their weights, and that's the definition of this L. Okay. So that's the lower bound, and all we used here is that we have a code that is a prefix-free code, so that we can draw the code trie and use Crafts inequality. But it also holds for Huffman codes in particular, because they're an example of a prefix-free code. The second part of the statement is this upper bound. If you have a Huffman code, it is never worse than h + 1. And for that, we do something similar, but we'll just construct such a code with a similar construction. We again define QIs, which are similar to probabilities, but they're defined by taking 2 to the minus and then this ideal quantity, log of 1/p, but rounded up because we can't really deal with fractional bits. Now, if you have a code of that length, its code length, it's L. The expected code word length is this. Sum pi times log of 1/qi. That simplifies to this, just plugging in. Same trick as before. It's the proper choice of the qi so that log becomes something nice. And here, not again. What we use is that if you take ceiling of some number, that's never more than x + 1. So if you use that here, we have the number is x, and then you split the sum. You sum up pi times log of 1/pi. That's exactly h by definition. And you're left with the +1. And that means what's left is the sum of all the probabilities, and that's 1. That's where the +1 comes from. So if we can construct a code where the code words have length log of 1/pi rounded up, we're good. That proves this statement. If we can show that Huffman codes are never worse than that. And what we'll do is we construct some code which is not necessarily a Huffman code that has these code word lengths, but then we use that Huffman codes are the best possible prefix-free codes, so they can only be better than that code. So we construct a code E prime, that has exactly these log of 1 over qi has exactly these code word lengths. And we construct this as follows. We do this inductively. If the alphabet has only 2 symbols, then there's not much you can do. You just assign each symbol 1 bit. But in that case, if you look at this, log of 1 over pi is that at most 1/2? That's a good question. That's at least 1 for one of them. Well, the code we use is a single bit. So clearly the cost of the code is just 1. That part's clear. For one of the symbols, pi must be at least 1/2. And so, all right, no, yeah, this is, pi is at most 1. So 1 over pi is at least 1. So log of this is at least 0. And unless one symbol is exactly never happening, which makes no sense. So we assume that that pi is strictly less than 1. So these are at least 0. So if you round it up, it's at least 1. And so if you take 2 to the minus this thing, that gets at most 1/2. Potentially it's smaller. And so then log of 1 over qi is at least 1 if you plug in that inequality. Good, fits together. So the base case is quite easy. In terms of the code, there's not much you can do anyways. If you have at least 3 characters, then we assume that they're sorted by weight. So A1 and A2 are the least frequent one. That's a trick you know from Huffman before. So we merge those 2 into 1 character, but now we assign it a new weight, which is just twice the weight of the second weight. So we make the weight a little bigger than what Huffman would have used. And then recurs as in Huffman's code. If those 2 are exactly the same, if the frequencies of the least frequent symbols are identical, then this does the same as Huffman. But if one of them is slightly smaller, then we know at least this is still summing to 1, to at most 1, because it's from Kraft's inequality again. So that means we can, instead of Q1, also use Q2, and we still get Kraft's inequality. So there was some slack in the rounding. Then we use the code that we construct from the recursive call. There we use the inductive hypothesis to show that this is true, this inequality. So the code word length of this E prime for this character is at most 1 over its weight, and the weight was set to 2q2. And that you can write as log of 1 over q2 minus 1 if you pull it out. And now if you remember what Huffman did, if you lump these two characters together and then recurse, at the end you have to split them again and add this last bit to distinguish the two characters. So that's what we do here. The code word in our constructed code E prime for these two symbols A1 and A2 is the code from before plus this one distinguishing bit. And so the code word for both satisfies this inequality again that we need. And that establishes the inductive step. So if you take that induction together, that shows you how to construct this code E prime that achieves that each code word is bounded by this log of 1 over qi. And then we use what I said before. So the code word length, the expected code word length of E prime is this. And that's at most the entropy plus 1 as we've shown above. And this is some prefix-free code. And Huffman is the cheapest prefix-free code. So it's at most as expensive as that one. All right, I think that was a long proof, maybe a bit more of than a sketch. But I thought it's insightful to show these two things. And in particular, the lower bound, I think, is quite nice and clean. It shows that no matter what you do with the prefix-free code, the entropy is essentially the bound that you get. You can't improve beyond that. I have a little question for you to wake up and join in. It's a quite tricky one, so I'll probably want to discuss the outcomes a bit as well. Any people? We get a few more. The miraculous appearance of people. We're neither in the room nor on the live stream. All right. Let me show the results. So there was quite a few votes for all of them. Almost. Several are right, but this one not necessarily. And I think the important part is what does yield more efficient compression? What I mean by that is kind of what's the best we can show. So if you compare Huffman coding with any fixed character encoding, which means like something like UTF-8 or ASCII, where you fix up front what are the code words that you will use for each character, and the lengths of the code words have to be the same for all the characters. Because both are prefix-free codes, remember, if you have a set of strings that are all the same length, they are prefix-free without any further paying attention. So even a fixed character length encoding, like we've discussed them before, is a prefix-free code, and so Huffman is never worse. So it's always better in the sense of less or equal. It's never worse. Maybe that would have been more precise. These two, when in terms of the bound that we can show, well, what we showed about Huffman codes is that the length of the Huffman code is at most the entropy plus 1. And if that's something I didn't show on the slide, but if you sum this up and all the pi are the same, then this sums up the same term all the time. Then all the pi have to be 1 over sigma. Oh, it's not a nice sigma. So you have 1 over sigma summed up sigma times, that cancels out, and what remains is log of 1 over sigma. Log of 1 over sigma. So that's the entropy if all the probabilities are the same. It's just log of the number of outcomes. So if we plug that in here, that's what we can always show. The length of this code, of this Huffman code, is at most log sigma plus 1. And so these bounds, because of that plus 1, it's not quite clear what happens. Now, because of fixed length character encoding is a code, you will never do worse. Strictly more efficient needs this condition though. So as long as you don't have this condition, you might be just as well. You might do as well with the fixed length code as with the Huffman code. If you have this condition, then there's an additional -1. If the entropy is less than log sigma minus 1, then this plus 1 cancels, and then so the best you can hope for with the fixed length encoding would be log sigma per character, but you need strictly less with the Huffman code. It's a little edge case in that question. Let's come back to Huffman coding for a second, because that's something I only verbally said last time. So if we encode with Huffman, there's several stages. Usually the first stage is you go through the text and you count how often do all the characters occur. And then you compute the Huffman code for these character frequencies. And then in the second stage, you go through the text a second time, and for each character, you replace it with its code word. The running time for doing that is sigma log sigma to construct the code. If you use a priority queue to maintain the symbol weights, so you maintain a partially built code trie, and the symbols can be these lumped together symbols, right? Remember these boxes that I drew around characters. And they each have a weight. And in each step, we take out the 2 with minimal weight. That's why it's 2 delete mins. And then we do 1 insert because we combine them and insert the sum again. That's where the, so you get sigma times that operation. And if you do a binary heap, as you've seen in Unit 2, you can implement those in log sigma time. If the characters come already sorted by weight, then you can actually do it in linear time with a neat algorithm using 2 queues. But if the characters do not come sorted, then you somehow have to sort the weights. There's to some degree you don't get around them. That's the time for finding the Huffman code. And the second part is easier. You just need to go through the text one more time. So you need to visit each character in the text, and you replace it with its code. For that, you can just use a table where you use the character as index. And then you get it in this time. So time to read the input plus time to write the output. That's the best one could hope for there. in practice, there's different variations of Huffman codes in use. Some comes from the type breaking rules. Some comes from the fact that you don't want to do two passes. Another thing comes from the fact that, well, Huffman codes are the optimal prefix-free code. They're not unique. You can do different ways. And so you can squeeze out a few more bits if you decide up front how you assign code words. But this is all around the question, how do you encode the Huffman code? And I promise we skip the details on that. So overall, what do we like and don't like about Huffman coding? It's an optimal prefix-free character code, and we always like optimal things because that sounds great. But you always have to listen carefully and check what exactly optimal with respect to what. So in this case, it's the optimal prefix-free character encoding. And it's very fast for decoding. You can use this code trie and just traverse then you're linear in the number of bits in the coded text. The two passes can be a bit annoying if you want something, if you want to do this. Suppose you're using this in a network router and you want to encode things as they come through. You can't wait, oh, hold back, just please scroll back in time and let me read that again. You might need to buffer everything, and that can be too costly. And also we have to store the code alongside with the text, which means if you're just encoding a short text, might actually be a bad idea to use Huffman codes.